So, good evening, students. I hope you're all fine, and I hope you're enjoying your second semester already. I welcome you back from your holidays, and now that you're back, let's start serious business. So, this semester, I was assigned the course unit, Ordinary Differential Equations, and I'm going to be teaching it first years. I think education and general and those doing economics and statistics, Bachelor of Science in Econ and STAT. Yes, so the course unit is called Ordinary Differential Equations. I'm sure this is not the first time you're coming across differential equations, especially if you did mathematics at A level. I'm sure these differential equations are taught in high school. So, as I told you earlier in the WhatsApp group, among the basics which you should know is 1. Differentiation. Given a function, you should be able to differentiate it. Or if I don't say differentiation, I can say that given a function, can you be able to find its derivative? That is another way of saying differentiating. And then another basic which you need to know is integration. Given a function, can you be able to integrate it? Okay, so you covered all these basics in high school, and in this course unit, we are going to be building on those basics. We are going to be using them as we deal with these differential equations called the ordinary differential equations. Okay, so let's start. The first paragraph here is saying that differential equations are having a vast influence in present research applications, especially in the physical, biological, and social sciences. So you can see how important differential equations are. They are saying here that you can find them in the physical sciences, for example, in physics and mathematics. Then in biological sciences, it's biology and social sciences. These are now the arts-related areas. And they add on to say that the complexity of problems posed by scientific processes leads naturally to mathematical models that have often called for a good foundation of differential equations. So you can be there asking yourself that how do these differential equations come about in the physical, biological, and social sciences? So this next sentence here is telling us that they come about indirectly in form of mathematical models. I'm very sure you've all come across this term, mathematical models. One instance is in 2020, when we had COVID-19 cases rising and used to see different researchers on TV telling us about what is going to happen in the next, say, 2 months, 3 months, that the cases will increase by this amount and so on. So those are the mathematical models, and those mathematical models mostly use differential equations as the foundation. If you don't know differential equations, or if you don't know how to solve differential equations or how to deal with them, then it will not be easy for you to come up with different mathematical models. So that's how special differential equations are. And as a result, differential equations have been adapted in many lifetime problems. That's what I was telling you. For example, the COVID situation in 2020, where now differential equations had to come in for people to predict what is going to happen, for people to predict the changes, how many cases are going to arise if people don't observe the necessary SOPs and so on. Yeah, so they arise in many lifetime problems ranging from mathematical designs for population studies. Those people who study population increase in different countries or in the world, they definitely use differential equations. They are able to tell that, okay, we are in 2022, but in 2030, for example, this is the estimated population that we expect to have. All those estimates can only be determined using differential equations. We shall also look at some applications as we continue with the course. Then another application is risk assessment in life insurance and banking processes. I don't know whether you've encountered this, but we have insurance companies, and for example, if you're starting a business, you can decide to insure whatever you're doing, your business and property, such that in case of any losses or fire and so on, those people can be able to compensate you in case such risks occur. So the risks, in case they have happened, can only be assessed with the help of differential equations. Then another application is epidemiological predictions. Now these are disease-related mathematical models. One example is the COVID-19. Then we have models for HIV, models for malaria, models for this disease in the Western Africa, Ebola. So all those diseases, people or researchers are able to predict what will happen or to come up with solutions using differential equations. And basically, differential equations is a study which is a truism that nothing is permanent except change. So differential equations tell us that change is a fact of life, just like you studied in your CRE. So everything that we have in life is subject to change. So we want to study that amount of change. By how much is something changing? By how much is the population changing? By how much is the disease multiplying? By how much did the fire burn? Whatever. So I just want you to understand that whatever you're studying is not just for purposes of calculating numbers or passing and getting A's, but just know at the back of your minds that these concepts that you are going to study have a lot of applications. Okay. So let's start now with the first chapter. And this first chapter, I'm just basically going to introduce the basic principles and the key terms and definitions that we shall be using every now and then. Okay, so what is a differential equation? So I have the definition here that a differential equation is an equation that involves derivatives of some unknown function. So you have some unknown function, and that unknown function has derivatives in it. So you want to use those derivatives to find the unknown function. And the second sentence here says that if the unknown function is a function of a single independent variable, then the differential equation is called an ordinary differential equation. What does this mean? You can have a function, say y, we don't know y equaling to something, okay? So several times, I'm very sure you have also come across equations where you have many unknowns there. For example, you can have y equaling to x squared. So in that example, y has only a variable x. But what if you have a function like y equals to x plus z? So the function y equals to x plus z has two variables, that is x and z, while the first function y equaling to x squared has only one variable, which is x. So if you have an unknown function y which depends on only one variable, and then you have derivatives involved, the equation that you have is what you call an ordinary differential equation. Don't worry, I'll look at some examples below. And for the case of having more than one unknown variables, that is what this sentence is trying to say, that if the unknown function depends on two or more independent variables, then the differential equation is called a partial differential equation. Okay. Then I noted something here, that suppose you have some unknown function y with a single variable. So since we have just one variable in this case, then we are talking about an ordinary differential equation. Okay, so then the derivative of y with respect to x. When we are differentiating a function, instead of saying that differentiating y with respect to x, you can also say that you're getting the derivative of y with respect to x. And mathematically, that statement can be written as shown here. You can have dy dx. This means you have an unknown function y and you're differentiating it with respect to x. So just seeing this dy dx, it tells you that you have only one variable, x. So this would form an ordinary differential equation. And dy dx, other mathematicians, if you don't want to disturb yourself writing the whole of this, you can just write it as y prime. So y prime or dy dx is the same thing. It means you're differentiating an unknown function y with respect to x. Okay? Let's look at some examples here. So in equation 1, we have y prime plus xy equals to 3. Equation 2, as you can see it here, and equation 3, equation 4, look at how they are written, and equation 5. So let me give you a minute to look at these equations before I proceed. Okay, I think a minute is done. So let's continue. So we are saying that in equations 1 to 3, equation 1, equation 2, and 3, the unknown function y is assumed to be a function of a single independent variable x. So from 1 to 3, we are assuming that we have an unknown function y which depends on one variable x. Okay? So in that case, you can as well write your y as y of x to mean that y is a function of x. just one variable x. And the functions y prime and y prime prime. We've looked at y prime. We saw that y prime is the same as dy dx. And dy dx means you've differentiated y with respect to x one time. Now what if you have y prime prime? So y prime prime means you've differentiated y with respect to x 2 times. Okay? So y prime and y prime prime are the first and second derivatives of y with respect to x. So if you differentiate the first time y with respect to x once, that means you're getting the first derivative. If you differentiate it again, then you're getting the second derivative, and so on. So that means the second derivative here, instead of writing dy dx, you write it as d squared y over dx squared. That means you've differentiated 2 times. If you differentiate the third time, then you would have d cubed y over dx cubed, and so on, depending on how many times you're differentiating. So we've said that from 1 to 3, y is a function of one variable x. Okay? Then that means the equations 1 to 3 have ordinary derivatives depending on a single variable x, and hence are called ordinary differential equations. So 1 to 3 are examples of ordinary differential equations because we have only one variable. We are differentiating with respect to just one variable. Okay? Now, what happens to equation 4 and 5? I want you to look clearly. In equation 4, we have u, and then down here we have t. But in the same equation, we have u, and then down here we have x. So this one alone tells you that this function u, the unknown function u, depends on 2 variables. And what are those 2 variables? One of them is t, and another one is x. So the moment you have 2 or more variables, then it is no longer an ordinary differential equation, but now it becomes a partial differential equation. Partial to mean that first you deal with variable t, and then you deal with the next variable, which is x. And even the way you write the partial is different. For the ordinary differential equations, we are writing dx out of dy with a straight d. But now you can see the way the partial is written. You write it with a curly d, a curved d. Okay? So 4 and 5 are examples of partial differential equations, and we can write them as I've demonstrated. So I see some mistake here. This was supposed to be Carlo. I always read it as Kali to u, to mean the partial, to mean that you're partially differentiating u with respect to t 2 times. So you'd write this symbol, this curved u, 2, then u over Kali t squared. Depending on whichever way that you pronounce that, that's how I pronounce them. Okay? So now you know the difference between an ordinary differential equation and a partial differential equation. Ordinary differential equation has only one variable. So in your differential equation, you have dy dx maybe plus y equals to 0. You will not have any other variable in the denominator of your derivative or differential equation. While in the partial differential equation, like you saw in this equation 4, you have u in the numerators, yet in the denominators you have t and then you have x. So this means that you have two variables. So that becomes a partial differential equation. Okay. Now let's look at the definitions. We have what we call order of a differential equation. What is the order of a differential equation? So the order of the differential equation, we are saying that is the order of the highest derivative which occurs in the equation. So given a differential equation, find out how many times the unknown function was differentiated. Okay? So the number of times the unknown function was differentiated, the highest number of times gives us the order of the differential equation. For example, in Roman number 1 here, we have dy dx. So the unknown function is the one which appears in the numerator. So the unknown function is y, and we are differentiating y with respect to x, and that is equal to x plus 2. So how many times was y differentiated? This is only one time because we have just dy dx. So that means since y was differentiated once, then the order of this differential equation is 1, or you can just say first order, to mean that it was differentiated once. While in the second one, we have d squared y over dx squared plus 2 dy over dx plus 3y equals to 0. The unknown function is this variable y in the numerator y, and how many times was y differentiated? So you can see here that it was differentiated 2 times because of this 2. Okay, so that means the order of this differential equation is 2, or you can simply say second order. In the third one, we are saying that this is the first order. I think now you can be able to tell the reason why. In the fourth one, it is a second order because you have y prime prime. As I told you, y prime means dy dx. Y prime prime means the squared y dx squared. So this is the second order. The fifth one is the first order. The sixth one is the second order. So that is the order of a differential equation. Just look at the unknown function and find out how many times it was differentiated. That is the highest derivative, and that will be the order of that differential equation. Okay, then we have another nice property. Let's see what it says. A differential equation can be written as a polynomial in the derivatives in which the powers of the derivatives go on decreasing. For example, before you look at a differential equation, I want you to look at an equation like x squared plus x plus 1 equals to 0. Write it down on a piece of paper. X squared plus x plus 1 equals to 0. What happens to the power of x? The first one is x to power 2. Then it reduces to x to power 1. Then plus 1. That plus 1 is the same as having 1 times x to power 0. So the power of x goes on decreasing. Now we can do the same when it comes to differential equations. You can have y prime to the power 2 plus y prime to the power 1 plus 6 equals to 0. So you have y prime is raised to some power, and that power goes on decreasing. Like you can see here, which example would demonstrate that clearly? Okay, here. Yeah, you have y prime prime raised to the power 3, and then y prime is to the power 1. So you can write the powers on those derivatives in a decreasing form. So now that leads us to the next term to define, and that is the degree of a differential equation. And we are saying that the degree of a differential equation is the power of the highest derivative appearing in the equation. So given a differential equation, look at the highest derivative. And by the highest derivative, we've already looked at when we are looking at the order. Look at the unknown function, and then from a given differential equation, point out the unknown function which has the highest derivative, and find out which power that highest derivative is raised to. Okay? An example is here. We have y prime prime the power 3 plus 4x y prime minus 3y equaling to x. So what is the order of this equation? We saw that the order, that is the highest derivative. Okay? And the unknown function here is y. How many times has y been differentiated? The highest. This is 2 times because we have y prime prime. So the order of this equation is a second order. But how about the degree? So since it is y prime prime, which is the highest derivative, then find out the degree to which it has been raised, or the power to which it has been raised, and the power is 3. So in this case, the degree of this differential equation will be 3. So to find the degree, just look at the highest derivative and then the power to which that highest derivative has been raised. Okay, now in these examples, we want to identify the order and then the degree of each of these differential equations. So the first differential equation is 3y prime equals to x plus 2. So the order of this differential equation, y has been differentiated once, so it is a first order. And to which power is this y prime raised? Y prime is raised to power 1, so the degree is 1. While if you look at this third one, we have y prime prime squared plus y prime cubed plus 3y equals x squared. The order of this differential equation is second order because the highest derivative is y prime prime. It has been differentiated twice. And looking at the power on y prime prime, that is 2. So the degree will be 2. While the fifth one, e raised to the power y prime prime. So the order of this differential equation is 3 because the highest derivative is y prime prime prime. It has been differentiated 3 times. But the degree, because when you look at this y prime prime itself is a power, okay? So the degree in this case does not apply. The degree only applies if the highest derivative is the one being raised to some power, not the other way around. And for the last example, square root of y prime plus y equals sine theta. We are saying that the order of this differential equation is 1 and the degree is also 1. Okay, so go through all the examples, discuss with a friend, and make sure you understand how each of these: first order, degree 1, second order, degree 1, second order, degree 2, how each of these answers came about. They can give you a differential equation and then they ask you to state the order of the differential equation or to state the degree of that differential equation. So you should be able to do that in case you're asked. Okay, so let's continue to the next item. So generally the equation, so you have an equation which depends on a variable x. This first x here means the variable, and these y's, we have y prime up to the nth derivative. So you have first derivative, second derivative, third derivative, and so on up to the biggest derivative. So you're assuming that the biggest derivative in this case is n. Okay, so you have an unknown function y which depends on a variable x. So if you have such an equation equaling to 0, then this equation is called an nth order. So nth order means the unknown function has been differentiated n times. Okay, so it's called an nth order ordinary differential equation. It is ordinary because we have only one variable x. Okay, and we add on and say that an nth order differential equation is said to be linear if it is of the special form, this one in equation 7. So equation 7 says we have n naught x y to power n. Now we are just trying to write a differential equation, an nth order differential equation, which means you have y prime n times, which we write simply as y to the power n in brackets. So this means that y has been differentiated n times plus something times y differentiated n minus 1 times plus blah 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 plus something times y differentiated once plus something times y. Okay, so this is the equation that we have. So we say that a differential equation is linear if it has this form. You go on, the number of times you're differentiating goes on reducing. Like in this case, we start from n, and the number of times you're differentiating goes on reducing up to 1. Okay, and these functions here, n naught x, a1x, an minus 1x, an of x, you can see that all these an's are functions of x. That's why I'm saying that these functions are independent of the variable y. So these can only be functions of the variable which we have, or they can only be constants. For example, you can have a 6 here, or a 1, a 2. So they can only be functions of x or constants. So if you have such an equation of this form, then we say it is a linear differential equation. Okay? So let's continue and see. Okay, now this, I think this I've already said it, that the functions ai of x, where I is from 0, 1 to up to n, the i's, the ai of x's, these are the terms, n naught of x, a1 of x, and so on, up to an of x. So you look at this index on a, starts from 0 up to n. That's why I'm having I from 0, 1 to up to n. Okay, so the functions ai of x, where I is from 0, 1 to up to n, are known as the coefficients of the differential equation. So the coefficients, those are the terms which are being multiplied by the derivative of the unknown function. So the coefficient of the nth derivative is n0 of x. The coefficient of the n minus 1th derivative is a1 of x, and so on. So these are just coefficients. We call them coefficients, just like in equations. If you have an equation like 3x squared plus 1, then we say the coefficient of x squared is 3, because that is the term that you're multiplying by x squared. Okay? Yeah. Okay. Then D says that if any of the functions ai of x, where I runs from 0 up to n, is a function of y, the differential equation in 7, because we call this one linear. But what happens if you have these coefficients? Because when you look at equation 7, we say this is a0 of x, to mean that this is a function of x. a1 of x, to mean that this is a function of x. an minus 1 of x. So the coefficients must be either functions of x or they must be constants for equation 7 to be a linear differential equation. But if the coefficients are not functions of x and they are functions of y, for example, that's what part D is trying to say, then in that case, the differential equation 7 will be a nonlinear differential equation. Okay? And if the function f of x in equation 7 is equal to 0, so you have a0 of x y to power n plus a1 of x y to power n minus 1 and so on equaling to 0, then we say that the differential equation 7 is a homogeneous differential equation. And if f of x is not 0, then we say that the differential equation in equation 7 is a non-homogeneous differential equation. Okay? Now, the next term. If all the coefficients ai of x, these coefficients a0 of x, a1 of x, and so on, an minus 1 of x, an of x, are constants, if they are all constants, then the differential equation is said to be a linear differential equation with constant coefficient. If they are all constants. Now, what would happen if some are constants and others are functions of x, for example? Okay? So that's what the next sentence is saying, that otherwise, if only one of the coefficients is a variable, then the differential equation is known as linear differential equation with variable coefficient. So the moment you have just one of these coefficients being a variable, then it will become a linear differential equation with variable coefficient. Even if the rest are constants, but just one is a variable, then it is a linear differential equation with variable coefficient. But if all these coefficients are constants, then it is a linear differential equation with constant coefficients. Okay, I hope that is clear. Now we have a note here which says that the term linear refers to the fact that each expression in the differential equation is of degree 1 or 0 in the variables y, y prime, and so on. So how easily can you tell a linear differential equation? Just look at the highest derivative. The power of the highest derivative should be 1. the power of the next derivative should be 1, and so on. Okay? Yeah. So the moment you have any derivative raised to some power, then that one is not a linear differential equation. We have some examples here. Y prime prime, this is raised to power 1, plus 5y prime, y prime is also to power 1, minus 6y, y is to power 1. So everything here, every power on the unknown variable and the corresponding derivatives is 1. Okay? So, first of all, what is the order of this? Let's go back to where we started. The order of this differential equation is the second order. What is the degree? We look at the highest derivative. It is raised to which power? It is raised to power 1. So the degree is 1. And we want to determine whether this differential equation is a linear differential equation with constant coefficient, or is a linear differential equation with variable coefficient. What is being multiplied by y prime prime here? So this is like having 1 times y prime. So you have a constant 1. While here we have y prime times 5. We have a constant 5. And here we have y times negative 6. So you have constants 1, 5, and 6. They are all constants. And this equation is being equated to 0. And we say that if the equation is equal to 0, then it is said to be homogeneous. So, in brief, we are saying that this differential equation here is second order, and it's a constant coefficient, linear, homogeneous differential equation. So all the coefficients are constants, so it qualifies to be a constant coefficient. Linear, because the powers on each of these derivatives, the y prime prime, the power is 1, y prime, the power is 1, and y, the power is 1. So it is linear, and it is homogeneous because it is equal to 0. While the second one is still second order, the coefficients are all constants, so it is a constant coefficient. Linear, because y prime prime is to power 1, y prime is to power 1, y is also to power 1, but it is not homogeneous because it is equal to 5. That's why we are calling it non-homogeneous. So I want you to look at the remaining two and find out where they belong. And we also have that the differential equations, the following differential equations are nonlinear. Let's see. We have x, y prime. Okay, y prime is raised to power 1, which is okay, because the definition says it should either be raised to power 1 or power 0. Okay, the definition here, that the degree should be 1 or 0 in these variables. Okay, now how about y? The degree should be 1 or 0 in the variables y, y prime prime, up to y to power n, the nth derivative. But now when you look at this, we have y is raised to power 2. So because of this term y squared, this differential equation becomes nonlinear. The same applies to the second one. Because of this term y prime raised to power 3, for it to be linear, the power should be 1. So because of this term, the differential equation is nonlinear. Okay. Now I want you to look at the remaining two differential equations and find out why we are saying they are not linear. Okay. And after that, you have this exercise 1 to try. State the orders and degrees of the differential equations. And exercise 2, classify the differential equations as to linearity. State whether they are linear What are the coefficients? Are they constant coefficients or variable coefficients? What is the order? Is it homogeneous or non-homogeneous? So you have these two exercises to try. So I think for now, I can first pause the video here. I'll make another video for section 1.3. Thank you for listening. I hope you enjoy the video. In case of any questions, feel free to ask me. Write your solutions down. You can post on the WhatsApp group so that I can have a look. I'll be glad to help. But I help after you've tried. Don't send me a message and saying, Madam, what is the solution for this one? I'll just block you. First try out before you ask me anything. Okay, bye-bye. See you in the next video.